are going to go further. Last time we studied about electromagnetic inductions, and the law that we are studying are two. There are two laws. First of all, we study about number one, Faraday's law on electromagnetic law. If you write in your exam Faraday's law only, I will not understand it because there are several theories from Mr. Faraday. Yeah, so you have to write Faraday's law on electromagnetic inductions. So this is the summary last time, which is not completed yet. Yeah, we just started. And the second one that we'll probably today or tomorrow, we will couple the Faraday's law with the Lenz's law. Not Lenz's law, but Lenz's law. So what have we learned last time? We learned that after derive the formulae on these pictures, based on this picture, we know that the work done last time is this one, right? Remember, this is the simplified versions of FGS, which you probably don't understand now, but will someday after your math teacher explains to you what integral is. So we just use F delta S. Okay, I don't require you to understand that at this moment. Now, F times delta S, and what is it again? The F, the force. That's right. Now you have to understand. If you see the rod there, is it the Lorentz force, or is it the force from you is meant on this word F delta S? Is it the Lorentz force meant, or is it the force from you? What if I give you a demonstration? I'm not sure whether you have learned it in your previous classes or not. If I want to move this chair, can I? Yes. But there's some work that I need to do. Why do I have to do work in order to shift, to move this chair? Why? Because this chair is bounded on the ground, especially because of the friction. Correct? So if I have to do a work, I have to do this, and I have to exert a force to the opposite directions as these frictions. Correct? So now, if this is my chair, the frictions is directed to me, and I have to give the end a force which is the same size like this friction. No, not true, not the same size. It can be also bigger. Remember? Yes? If the force has the same size like the frictions, the chair will move with a constant speed. But if I exert a bigger force than the frictions, what happens? It will move accelerated. Very good. Who says that? Newton's law number?
3.
3. Thank you. You learn from your mistakes. This is Newton's law number 3.
It's not as my 3. Because I can't do that.
Now, what about this? Is the word meant here? Is the word because of this force or because of the Lorentz force? Yes, ma'am.
That force.
Because of my force, the force from us. So why do you need to do this force? to overcome this Lorentz force, correct? And I have explained to you what is a Lorentz force. For every reaction, there is a reaction, right? Good. Now, this is exactly what is here, although then we use B times I times L for the force, which is, at least we assume the force we exert, the force that I need to do this work is at least of the same size like the Lorentz force. Can it be bigger?
Yes.
If you want to. Yes, it can be bigger. So then I just use this. This is the Lorentz force, but be careful. In the exam, I will point out, is this the force you mean? Or is this the force you mean? No, this is the force I mean in my work, because I do the work. Not the Lorentz force is doing the work. Okay? I do the work. In order to shift this rod further, certainly you cannot say who starts, because this is actions, reactions, right? By the time you start exerting this force, suddenly there is a Lorentz force. Understand? When I don't do anything, there is no frictions. At least there is no glide frictions, glide variable. There is half variable, but there is no glide variable. Have you heard about that? There is also called the static variable or static frictions, but there is no kinetic frictions. But once I do something, suddenly the ground says, no, I want to oppose you. So these actions, reactions cannot be told who starts and who reacts. I can say he starts and I react. I can also say I start, he reacts. Understand? In some problems, it might be clear cut. For instance, if I do this, siapa yang gara-gara? Kamu. Who do the opposite force?
The wall.
The wall on me, right? It's clear cut. It's also actually here clear cut. It is who starts, and then the Lorentz force reacts, and that's what the last law said. And that's exactly with these proverbs that I have in Bahasa. Do you still remember? Cina, merpati. Right? Okay. Now, if I go further with the formulae, I have then BL delta S. Can I erase this first?
Yes, you may. Did I? Oh, yeah.
And then I will come up with the last formulae, which is energy is BL delta S, BL delta S, and I will explain to you that I and I cancels out. So I and I cancels out. So I have BL delta S over delta T, which is just B times L times V, constant speed. Why? Because the force here and the Lorentz force there, Lorentz force here, the force there have the same size. That's why it's a uniform motion. Now, this PLV can be further explained L times delta S over delta T. Can I write again? PLV, this delta S over delta T, this one can also be considered to be delta area. Why delta area, so I cannot understand it.
What's the area?
Area of the motions of this. This is L, and this is the delta S that this rod has taken, has traveled. So this is the area that he had after he moved in these directions. Okay, that's the area of the motions of this rod. Now, this is the delta A over delta T. So in one way, sometimes you need this formula. In another way, sometimes you need B, L times delta S becomes B delta A. And B times delta A usually put together, and you want to give a new name for this. You want to give a new name for this. What's the perfect name for B times delta A? Yes, ma'am.
Magnetic flux.
Magnetic flux. That's right. B times delta A has a name.
I didn't
Magnetic
know that.
flux. Der magnetische Fluss. Magnetische Flussdichte mal diese heißt auf Deutsch
Wait, Pato, what is that? The B?
B,
Why is there
magnetic
the other
flux.
one? I know what that is. Tapi kayak, why is there like a
This one?
last one? Atas. Yeah.
Yes, this is irrelevant. I just use B times delta A. And this B times delta A, I put it in bracket because it has something
Oh.
special about it. B times delta A, B, magnetic flux density, der magnetische Flussdichte, delta A in English, the change of area, because here to here, the area within the time, change of area within the time, and in German, der Flächeninhalt, oder der veränderliche Flächeninhalt, correct? Now, magnetic flux in German we call it der magnetische Fluss, the magnetic flux. Okay. Now, if I have B delta T over so delta A divided by delta T, then this is no longer only magnetic flux, but rather it's called change of magnetic flux because in terms of delta T. Just like whenever you have delta S over delta T, in other problems, if you have delta S over delta T, this is change of distance you travel, which is then you know it as a velocity or speed, right? Now here is not magnetic flux anymore, but rather change of magnetic flux. Change of the magnetic flux. And that's basically the main idea of Faraday's law on electromagnetic inductions. Electricity, current, and induced EMF can be produced if you have a change of magnetic flux. Once more. Electricity, induced EMF, and induced current can only happen if you have a change of magnetic flux. And if I have to explain that to professor or university students, that's enough. The change of magnetic flux will create electricity, will induce EMF and induce current. But then, for us now, in our classroom, it's much more better if you use the explanation of trigonometry. Oh, because there is a relative motions between the magnetic field and the electron inside the conductor. And that is exactly here, change of magnetic flux, even though not only. Actually, what she explains is not only the only way. You get it with me? Change of magnetic flux is not only because of the relative motions, magnetic field, and the electrons. There are several other ways to do that, but it's enough for us in this level to just explain that. For the higher level, this is the best explanations. Change of magnetic flux creates electromagnetic inductions, create electricity, creates voltage or induced EMF. Are you with me? And that's exactly the keywords that my students, if they don't understand it, that's the keywords of every Nachhilfe Schüler von mir, whenever they want to take IGCSE, AS level, they just memorize this word. Because that's the keywords every examiner wants to find, including me. Okay, everyone, if you don't understand it, just memorize it at least. Yes, this keyword. Are you with me, guys? Yeah. All right. And also in the mündliche Prüfung, I'm expecting this word more than anything else. All right. Okay. One more, which is not here. Unfortunately, not here. One more. Everyone, this E, as I said to you, I don't like this E, right? You still remember what is my favorite letter for the English area? Epsilon. Epsilon, very good. Epsilon. Induce epsilon, induce EMF. It turns out after several research, not only B times delta A, here the change of magnetic flux is happening because of the change of area, but it can also be not only because of the change of area that this change of magnetic flux take place, but it can also be that the area stays the same. I will explain to you through examples what does it mean. It can also be that the area constantly the same, but I change the magnetic flux density. Also happens. So actually there are two main ways to create change of magnetic flux. There are two main ways to change magnetic flux. First, you change the area of the coil, of the conductor, of the motions of the moving conductor, and change of magnetic flux density. I don't see it. 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 I don't see anything. Yes. Divided by delta E. And that is epsilon. Okay, everyone? This is only part of. This is only part of. Yes, ma'am.
Can you explain again what the delta area is?
Okay, delta area.
She just realized it's going to be
If this is a rod, or here. If this is a rod and this is the magnetic field area, this is the magnetic field where the magnetic flux or field really rush on it. So now this is the conductor, right? Just imagine this conductor is just a line. Now change of area means how big the change of the area that this conductor has taken. Now, certainly there is no area actually. This is only a line, right? But concerning time, in respect to time, actually it has created an area. So in respect to, let's say, 10 seconds, this rod actually really create a traveled area, which is this line, the length here, times this width. Correct? So delta area means, in this case, is the change of area due time or in respect to time. Understand? How far the traveled area.
Delta area is why it's delta x divided by delta t.
Yes, delta s is the change of distance, but times the length here, times this length,
This time.
then delta A, delta area. Understand?
Yeah.
Okay,
Thank you.
yes. Now, keep it in mind, change of magnetic flux can be both because of this change of area or because change of magnetic flux density. I will explain to you through examples. I know it might seem now unreal to you, theoretical to you, but it will be explained soon. I already prepared some papers. Now, for us physicists and mathematicians, I don't like this. And we invent, unfortunately, a new letter for change of magnetic flux that includes these two processes, that includes these two things. And can you find it for me? What letter or what specific letter that the mathematicians use for B times delta A and A times delta B? 1 minute. Research on your book. Be a friend of your book. It's on page. It's on page 283. How do you call this? Huh? No. One letter that represents this. What is the weird letter that you see for the first time there? Yes. Yes. Okay. This B delta A delta B. Now, for mathematicians, is replaced by delta V. It's just a short annotations for these two things. And then divided by delta T. Usually, at this point of time, or this point of lesson, I usually direct this to differentials. But I know that you have just started with differential, correct?
Yeah.
Or have you done it last year?
What's it in German?
Applied.
Yeah, we did that.
Now.
Last year.
Last year, at second semester.
First and second.
Yeah, first and second.
Second was offline, so.
First and second semester, both of them. So basically, the best formulae, not delta. I don't want to explain because I'm not math teacher here. Actually, the best one is differential of flux P with respect to dt. That's the best formula. So it means phi now is the divine physical quantity B times A. Seems very theoretical to you, I know, but in 1 or 2 lessons you will be acquainted with this and feel like, oh, that's not bad at all. Yes, it's totally easy, don't worry. Yeah. All right. Now, we want to read together this paragraph. Okay, we want to read together this paragraph.
Which paragraph?
This one, the one that I showed you. Everything okay, Yasmin? Any questions? I know it's hard. I will give you an example soon, yeah? Now, who wants to read? Sister Kaira? Sure.
The product of the magnetic flux density and the area A is called the magnetic flux.
And how do you write it? Using the Greek letter of, you know what is names of the Greek letter? How do you call it?
B.
I thought I was close.
I know that I don't allow Francis to talk in Greek, but today the only Greek word that you are allowed to use is this one. V, magnetic flux, the product of B times A. B times A. A little visit to your differential. If you have dUV to dt or apply term from U times V, have you used U and V in the product regal? Forgotten?
No.
Lost in translations? Lost in memory? Habt ihr gewusst, dass diese U und V, wenn man ableitet im Produktregel, what is the product rules, product rule. U Strich V plus U V. The product rule says if you have a product of two terms and it is differentiated, differential, what is differential, what is it for? You can ask Mr. Isaac Newton or Mr. Leibniz for you, as he is the founding fathers of this calculus. If they're still alive, they will help you. If not, then you have to watch many YouTube movies or read a book. Right? Now, look on this again. D, B, A, dt. It's just basically B times A x B mal A. It's just like U mal V. Abgeleitet. Correct?
Yeah.
Are you with me, guys?
Yes.
Yes? So what is the Ableitung again? From B and A? B axon
Yeah.
times A. Is it the same like this?
Yeah.
Yes.
Plus B A axon. Correct?
Yeah.
Now look, B axon is just dB dt times A plus B times dA dt. So this is from physical explanations, this is from math explanations. Understand?
Yes.
This is the product rule. And this is exactly what I just said just now. Okay, you read further if you finish writing. Yes?
Can you the board?
Oh, yes. Several sentences and then we are ready to see some examples. Okay, after this. Now, Kyra, if you finish, then you may read further for us.
Oh.
Okay.
Yeah.
Check. That's exactly the same idea.
Oh.
Sister, the concept of magnetic flux is very useful for calculating induced EMF. The example.
The example of the conductor cutting across the field lines shows that the induced EMF is equal to the magnetic flux swept out by the conductor each second.
Sweat out. Überstreichen, sagt man das so?
Ja.
Überstreichen, ja. Die überstrichene
Fläche.
Fläche.
Ja, genau.
The sweat out area. Die überstrichene Fläche. Is it clear, everyone? Oh. Is it the actual lesson?
Yes.
Just one, 2 seconds, please. Make it to end it. The example of the conductor across shows the induced EMF equal to the magnetic flux swept out by the conductor each second. Can you read further?
Michael Faraday was the first person to show how induced EMFs could be calculated from magnetic
Yes. Magnetic flux, you know? One word. Flux linkage is a new term. It's just a product of Phi times N. The number of coil is just a divine physical property. Flux linkage. Okay?
Okay.
See you tomorrow with 7 examples. Have this paper. Thank you, everyone.
Have a good weekend.
Not bad. Just,
Is that still recording?
yeah. I'm switching up first.
But it's not even joking, isn't it?